the invitation. So I'll talk about locally decodable codes. LDCs. And it's a bit of a survey. It's something I've worked on for many years. Probably one of the first thing I suggested and one of the first problems that I was handed, and it's still pretty wide open. I think it's I'm going to focus here on the kind of the linear algebraic setting where we have a field and linear maps, and the questions that are going to come up, again, the questions that are open for several decades are, you can think of them as really basic questions in geometry, finite fields over the reals, over the complex numbers. And there's another view of these codes that is more kind of binary alphabet and information theory, and I'm not going to go there. It's a whole different, it's also very interesting, but so I'm going to focus on kind of the linear algebra view of this problem. So if you know about the other side of things, then don't I hope you don't get very upset. Okay, so I'll start with the definition. We have two definitions. The first one is the more standard definition, where we have an error correcting code and a decoder that makes queries. And then we'll see an equivalent definition that's just using linear algebra. So this is the definition one. So you have a linear map. And feel free to stop me with questions. Linear map from f to the k, where f to n to f to n, or f can be any field. And we said that this map is T delta LDC if the following, I'm going to draw a picture here. So think of this as your message X. It has k coordinates, and it gets mapped by E to a longer encoding. So we'll see in a minute, it's an error correcting code. It has to stretch the message by something. So this is E of X. And then there's some noise that's added. So the noise in this case is, will be some places that are corrupted, and most places will be correct. So this will be some string Y, and we'll assume that Y is close to the encoding in Hamming distance. So it's at most delta fraction of errors, but they're arbitrary. And then we would like to be able to recover. So typically in an error correcting code, we just want to be able to recover X from Y. That's the standard kind of delta error correcting code. But here we're asking for something stronger. We're asking that there's a decoder D. Let's think of some probabilistic algorithm that gets as input I in K. So some coordinate of X, and is asked to output only Xi, but without reading the entire Y. So D is only allowed to make T queries to Y that's close to E of X. And think of T as very small, so 2 or 3, 4. And after those queries, which can be randomized, it has to output Xi, and again with high probability. So let's just fix the probability here to be 3/4. It doesn't really matter, as long as it's better than kind of random guess. It's fine. So we'll just fix it to 3/4. So think of delta as some constant. Again, delta doesn't matter. It can be any constant. We're not going to worry about it too much. We really care about T. So in this setting, we'd like to fix T. Let's say 2, 3, so on, and ask how small can n be. So n is a function of k. So we like infinite families of codes where k grows, and n. So ideally, maybe n can be polynomial in k for some fixed t. Okay, so we don't know if that's possible. So later I'll try to outline the best known constructions and the best known lower bounds, and you'll see that they're very far. And in particular, we don't know if you can have polynomial k even for any constant. So that's kind of the biggest thing open problem. And you can imagine this would be something useful. And in practice, I think the most famous example is maybe on CDs and DVDs where there's some corruption, there's scratches, and you want to quickly recover the next block to play, and you don't want to read the entire CD for it. You want to make a few queries and quickly figure it out with high probability. So, but there are also, I mean, aside from practice, you can do about storage, things like that. There's theoretical applications of this. It actually came up in complexity theory in the 90s, in hardness of amplification, pseudo-randomness. It's related to privacy, cryptography. It's kind of, it shows up in a lot of different places, and the constructions of these codes are very, they're needed, but again, the constructions that we know are not very good. On the other hand, the lower bounds are also not very strong, and the lower bounds themselves also sometimes have applications, kind of theoretical applications. So it's a really neat question, and then you'll see in a minute that you can state it in a way that doesn't involve any procedures and any, something very linear algebraic, a clean problem. So let's see. Any questions on this? Okay. So see. Maybe just to make this very, very clear, I'll just say that here we require that for every x, for every y, with y minus d of x in Hamming distance is most delta n, and for every I, d y is xi is quarters. So, and again, d makes it most t queries to y, but this is really worst case. No, there's no randomness over x. If you had randomness over x, it gets much easier. This is for every message, for every encoding that's close to for every y that's close to the encoding, every coordinate has to be able to recover it with high probability, and the randomness is only over the choices of these t coordinates. And in general, this d might be adaptive. You might make one query, see the value, and then decide what the other query is. But you can show that, in fact, with some constant loss in delta, which we don't care about, you can make d non-adaptive. So d just picks some t tuple according to some distribution, and then reads the values. And in fact, you can also assume, because e is linear, you can also show that d has to be linear. So d just computes some linear function of the queries. And this is what you see from the second definition that I'll write down. It's equivalent up to a loss in delta. So let's see the second definition.
I'm sorry, so the noise isn't random. You just have
Worst case, for every y that's close to e of x. So it's adversarial noise.
Okay, that's not part of the probability.
If you make it into random noise or even erasures, it's equivalent because of this second definition.
Okay.
The second definition will show you that it's actually the same for any noise model. Questions? That's a good question. All right. So here's an equivalent definition. So I'm going to say that a T delta LDC is a list, an ordered list V1 up to Vn of elements in F to the K. We have n vectors, numbered vectors. Each one is in F to the K. Such that for every I in K, there exists a T uniform matching MI on N. So MI is a set of disjoint T tuples of these vectors, such that, first of all, there are many of them, and they're disjoint. So there are at least delta n disjoint T tuples. And two, for every tuple T in MI, this is some T tuple in the ith matching. The ith standard basis vector, so this is just zeros. One is in the span of Bj, J is in T. Okay, so there's a lot to parse here, and this is really going to be useful later. So let's just think about it. We have a bunch of vectors. For each I, for every coordinate, there's a large family of disjoint T tuples. So, yeah, it can be, let's see if T is 3, maybe these three, and so on, such that every tuple in the ith matching spans the ith standard basis vector. I should oil this. Okay. So the definition clear. I'll try to argue why they're equivalent in a second, but just in terms of parsing it, yeah.
So every tuple has to span one of the.
Right. So for every I, we have a family of tuples.
Okay. Yeah. No.
Mi. In this Mi, all the tuples span Ei.
Okay.
Okay. So let's just try. So one direction is easy. So if I have such a family of vectors, what would be the corresponding linear map?
Matrix sets.
Right, this would be the rows of the matrix. Or in other words, if I want to show that definition 2 implies definition 1, I can define E of x to be Dj in a product x, J in n. In other words, the mapping E of x has the rows V1 up to Vn. So you compute it's called the generating matrix of the code. And then what would be the decoder? What would D do?
Use the matching.
I use the matching, so
just take a matching edge without an error and take the coordinate from its span.
Right. So if we knew what the errors were, we could just pick a tuple in MI that has no errors. And then because these rows span EI, the inner product of these rows with X would give me XI, right? Right. So if I have let's say sum J in T, Cj, Bj equals I, then I can just take the inner product with X and I get that sum J in T, Cj, Bjx equals Xi. So any tuple in Mi gives me T places that determine Xi. And because there's so many of them and they're disjoint, I can, well, if I know that there's less than delta n errors, then I know that there has to be a tuple that's not in the set of the errors. Then I can just use it. But if I don't know where the errors are, I can just pick one tuple at random. And with high probability, I will land outside of the error set because, and I can lose a constant factor in delta. So I replace delta with delta over t or something like that. So I lose a factor of t, and again, t is a fixed constant, so that's fine. And this also shows you that kind of erasures or random errors or adversarial errors are all the same, because once you have this structure, you can deal with any one. And okay, and then the other direction is a little more tricky. So let's say if I have a code, you have to show that there exists such a matching. This is done kind of iteratively, saying well, there has to be a tuple that spans EI, then just add noise there, and then you find another one and another one and another one, and you just have to make it formal. But this is the reduction. All right. So now we have a question about the arrangement of points in some space. And again, I'm going to allow F to be any field, to be the real numbers. So we'd like to have some points that have some linear dependencies and they span certain vectors. And the question is, how many points do you need to get this? How large does n have to be? Are there small sets with this that satisfy this, or do all these sets have to be large? So let's see an example to code. Well, the most famous example is Hadamard code. And it's a two-query code. By the way, from this definition, you already see that T has to be at least 2. T is 1. This can't really happen for large K because every VI, if you look at one tuple, so if the MIs are just sets of size 1, and every element in MI has to span EI, then it can't span another EI. It has to only be an MI. So then you can't have more than 1 over delta different I's. So K is basically fixed. So T equals 1 is not going to happen. But T equals 2 already, there's an interesting construction. And in this construction, N is 2 to the K. The code is very simple. F X is all the inner products with binary vectors. Think of this as a subset of any field. There's always 0 and 1, so I can do this. And the decoder is very simple. Let's just call it B of I. So to recover Xi, I'm going to pick a random V equals 0. And then I'm going to query the two positions, V plus I X minus. I'm making two queries. Each query individually is well, it's uniform over a large set. So I'm really picking an edge in a perfect matching. Right? I look at all the coordinates. I look at all the pairs where they differ in the ith bit, and I'm querying both. And from those, I can recover Xi. Right? So it's pretty simple. See, delta has to be some constant, like 1/8 or something. Now I finish. Okay. So obvious question is, can we do better? So n is exponential in k, and we ask, okay, can you have polynomial dependency, okay, maybe linear? And for the case of t equals 2, the answer is no. This was the first paper to show this was Goldoy, Shilevitz, Schumann, and Trevisan for binary codes, and then in the paper with Amir Shpirka, we extended it to codes over big fields. And I'll show you a proof that's that I think is new. I just kind of found it recently, and I don't think it's written anywhere, but it's to show something something new. It uses some nice inequality from analysis. So let's prove that you can have better than 2 to the k. So here's the proof. So step 1. First of all, okay, let's just say we have what we have. We have vectors v1 up to the n, and we have matchings mi that are pairs, and for every pair, so j prime is an mi. There's some coefficients alpha vj plus beta vj prime equal vi. So there's some alpha and beta, and I don't know what they are. They could be in any field element. So the first step, I'm going to reduce the case where alpha is equal to minus beta. So why is this good? If alpha is minus beta, it means that every pair points, if you look at these two vectors, their difference is proportional to ei. So it means that they only differ in the ith coordinate. It's a very strong condition. It's a very combinatorial condition. And then we'll use that once we know that, we'll finish the proof. One thing I didn't say here. So in general, these VIs, they don't have to be distinct. However, for this lower bound and for other lower bounds, it makes life much easier to assume these are distinct points. In general, if you really want to prove things, you have to work much harder to deal with the case where they might be repetitions. And it's actually an interesting open problem to show in general that repetitions don't happen, but it's not known. So I'm going to assume they're distinct. Okay. So how do we reduce to this case? Well, we can look at each Vj can be scaled. We're free to scale them because we only care about their span. So we can scale, just multiply them by a scalar, each Vi or each Vj, such that the first non-zero element is 1. Just multiply each Vj by some constant so that the first non-zero element is 1. And now, if Vj and Vj prime span ei hat, there are 2 cases. This one is that one of the Vj, other Vj or Vj prime has I as their first non-zero coordinate. So let's say Vj. So this is the ith position. And then Vj prime can be, it can have, it could have 0 here or not, but so we don't really know. And this case is problematic. We don't like this case. However, this case can happen too often because Vj can be such a bad occurrence only in one of the matchings. So there are at most n. If you look at all these matchings together, there are delta n times k edges. At most n of them can come from such a bad thing. So we just throw them away. And that's okay, it's negligible. Also because the proof will show only uses the sum of the sizes of the matchings. We don't need each one to be large. So it's okay if some of them become small, but overall we go from delta n k edges to delta n k minus 1 edges. Okay, so this can't happen. This is at most n edges in total. And okay, and then the second case is where we can get alpha to be minus beta, because in this case, the first non-zero coordinate is less than I in both of them, and then it has to be the same in both, because otherwise this wouldn't cancel. And then alpha is equal minus beta, because this has to cancel. Okay. So good. So now let's see. Now that we have this extra condition, so instead of any linear combination, we have differences. Now we can try to prove it that n is exponential in k. So let's suppose only case 1 happens. So every pair in the ith matching is a pair of vectors that differ only in the ith coordinate. So I'm going to look at projections along the ith axis. And these points will basically collide when you project them. But I'd like to do this, I'd like to use the Loomis-Whitney inequality. So I need to work over the real numbers. So how do I, so this is an arbitrary field. How am I going to move to the real numbers? Oh, we're just going to map the elements of the field arbitrarily into the real numbers. I don't really care. So let's embed F into R. Just, well, I guess I have to worry about. So I only think about finite fields and R or C, but I guess I have to worry about fields that you can't embed into R. But let's forget about this for now. Let's say F is either a finite field or R. In some, so you embed it in some way. Just and then you look at the projection maps from RK. RK minus 1. So notice when we embed it into R, we keep all these properties, the two vectors that differ in the only in the ith coordinate, they still differ only in the ith coordinate when you replace the entries with real numbers. So, so if I look at the ith projection, what do I know? Know that the size of the set there are delta n edges that collide. So this is at most 1 minus delta n for every I. So I shrink in a lot of this projection, in all of these projections. And there's something nice called the Loomis-Whitney inequality. which is much more general. It applies for functions, but I'm going to use it for finite point sets, which is legal. It says that if you have a set, a finite set, it doesn't have to be finite, but let's say specifically for a finite set in RK, the size of S is at least the product of these quantities here. So S divided by the size of the projection, and so this is called the width in the ith direction. This is one way to think. If you have a body and you project it, and you divide the volume by the volume of the projection, it's kind of how wide is it in the ith direction. So the set is at least the product of the width. It's one corollary of the Smith inequality. So here we have a set of size n. These are at least, it says n over something that's less than 1 minus delta n. This is at least 1 over 1 minus delta to the k. Delta k. So you get something, doesn't matter, something exponential in k. And that's essentially matches the Hadamard. Maybe there's some constant here, but at least you know they can do better than exponential. Sorry. Right, so the questions? Right, so now the natural thing to ask is, where can you do something for 3 queries in this way, right? So let's just let me just state the question, and again, you can think of it over any field that you like. I'm going to state a problem that would imply the 3 query lower bound, but it's stated in a way that's a little more geometric. So the question, let's say you want to be n such that no 3 in a line. Think about the real numbers, might be the easiest case, as far as I can tell. Suppose that for every I, look at the projection, I at the end. Look at the projection, you suddenly see a lot of collinearities. But they're in a way that's disjoint. You see many disjoint collinear triples. Suppose this projection, for every I, this projection has, say, it's a linear number of disjoint collinear. You can massage this problem to look like this. This is just a nice, I think it's a really nice way to think about it. If you're interested in problems about collinearities and incidence and so on. And show, what do we need? So we'll see later. The best bound in general for this problem, if you allow any field, is k squared. So to state an open problem, I'll make it 2.1. So show something better than a square. Small fields, there's a recent say f is, let's say, much smaller than k. There's a recent cubic law bound. And so if you like to beat that one, you need 3.1. So just what's open. And then we'll see that the upper bounds, we'll see in a minute, are kind of very super polynomial. So we don't really know what the truth is. Okay, so we just say we have a bunch of point nodes in a line, and in every direction that you project, you get many collinear triples that are disjoint. If you drop this, then nothing is. It can be quadratic. You can think about an example where you just have many collinear triples, but they're not disjoint. You can get a quadratic structure. So
give you t equals 3.
yes, this is for t equals 3. Yeah, and you can think for t equals 4. It'd be again.
Just replace the 3's with t.
Yeah, you'll get 4 coplanar points for every projection, and then you would have to beat 1.5. All right. Okay, good. So again, I'll show more constructions and more log bounds as we get closer to lunch. But now I'd like to show you a variant of this that's very interesting, and it basically amounts to allowing, instead of points, allowing for arrangement of subspaces. Which again, that's something we do often in other problems in incidence geometry, in other type of problems where we generalize from points to higher dimensional objects. So you can do the same thing here, and it actually has a meaningful interpretation in kind of real life. And that's pretty cool. And also leads to some nice open problems. So okay, I'll just write them. I'll write it again. So this is it's a variant called, has I guess 2 different names. It's LDCs. Locks. And another name for this is peer, which is a private information retrieval. So this is, it sounds very applied, but let's see what it is. So again, we had 2 definitions. So I'll repeat quickly both definitions. So in definition 1, remember we had a linear map from Fk N. And we had X, E of X, we had the noisy Y, and then we had the decoder that makes queries to recover Xi. Here I'm allowing the alphabet of the output to be partitioned into blocks. So this is F to the L to the N. So instead of having N field symbols, I have N blocks of L symbols. So again, I have blocks of size L. And D still makes T queries. But each query now is a block of L bits, or L field elements. We get T blocks. And the definition is the same. You make T queries, and you have to output Xi. You get I, you query T blocks. Think of L as 2 or 3, also some. It might be small, or it could be growing. And you have to output Xi with the same probability. And in the second definition, you get a question about arrangements of subspaces. So you have L dimension of subspaces. Let's call it now big V. And again, for every I, we have a T uniform matching MI. That's at least delta n tuples. And for every tuple, if you look at the tuples, the subspaces indexed by this tuple, and you take all of them together, they would span EI. It's just, so you just can write there is a sum of subspaces, or just the span of the union. So yeah, you can pick one vector from each of these T subspaces and that together would span EI. And again, the same proof kind of shows that these are equivalent. So this is the definition. Clear. Because I'm just allowing for blocks, but suddenly this becomes interesting because here for okay, let me first say why this is. Where did this come from and why is it interesting? So why do we call this private information retrieval? So here's why. Think of it kind of the following story that you have a user and there's a database X. Think of it as a list of phone numbers or addresses or something. And the user would like to retrieve some entry in this database, but the user doesn't have the database. It could be a giant list of IP addresses on some network. So the user would like to retrieve this, and this thing is, let's say, stored on some server. So the user would like to retrieve this without revealing I to the server, because it might be private, might be a secret that the user wants to contact that person. So this is, it's a kind of a cryptographic problem, and you can solve it using cryptographic tools, and there are many open problems even there. But you can think about using one-way functions or things like that, zero knowledge proofs or whatever. But now I'm talking about the information theoretic setting, where we really like to give no information about I. So this is so the only way to solve it is basically to ask for the entire database. However, if you have more than one server, let's say X is replicated. This is server 1 and this is server 2, and they don't communicate. You assume there's no communication between them. The user would like to exchange messages individually with each server, retrieve Xi, such that each server individually has no information about I. So that's already seems like it might be possible. So basically, you want the user to send a question to server 1 that's just like a random string, and another message to server 2 that's a random string. But you'd like to correlate those random strings in a way that depends on I, so that the answers could be used to recover Xi. So that's a two-server private information retrieval scheme. This is what the information theoretic setting.
It's related to the secret sharing matrix, or?
It's related to secret sharing, but it's complicated. It's not directly, but obviously there's some secret sharing is kind of related to it. What would you like to minimize? Like to minimize the total communication, the number of bits sent back and forth over both interactions. So what does this have to do with LDCs with blocks? Well, if you have such an LDC with blocks, the user can basically send one query to the first server. So let's say you have such a two query LDC. The user can pick a random edge, say JJ prime in MI. Let's suppose for a second that the matchings are perfect matches. So each query is a uniform, each J and J prime are kind of uniform strings. So they don't reveal any information, and the user can send J to the first server and J prime to the second server, and get back the Jth position. So E of X J and E of X J prime. And from these two values, the user can recover Xi. Right? That's exactly you're just simulating the decoder. But again, if these are perfect matchings, each query has no information. If there are big matchings, then there's very little information. You're asking kind of a random location. So again, for this application, you really want this to be perfect matches. But again, up to this technicality, that it's the same question. And what's the communication cost or the cost of the protocol? It's so in terms of that code, what is the cost? The user sends log n bits, log base 2n bits to each server, and gets back L times log size of f. Again, we'd like the field to be finite for this. So we'd like to minimize this. So in this case, even so even for two queries, so we saw that for two queries without blocks, we know exactly the answer. It's 2 to the k. For two queries with blocks, we don't even have that. We have nothing. So I'll try to tell you what's the best thing that's known, and I'll finish kind of this part of the talk with an open problem that's in that sense about incidences that's related. So what's the best? Focusing on two servers, but you can ask this for 3 servers and so on. But even the case of 2 servers is wide open and very, very interesting. And people do care about these things. I mean, if you had a really good construction, you would get, you could think of cases where you would implement this. It's a distributed setting where you'd like to have some privacy, and it's been we've tried to implement it, just the constructions are not good enough. So the best upper bound, best construction is so L is square root log k, and is I'm omitting like doubly logarithmic things, but something like this. And you basically get the, so this is for a small finite field. So both of the terms there are basically the same. And this is trying to work with my former student copy from 15. And I'll mention the codes where this comes from. So this comes from a family of actually from 4 query LDCs without blocks, and then you can kind of half the number of queries by adding bigger block. But we'll see kind of where this comes from in the second half of the talk. And the best lower bound so we have the total communication is at least 5 log k. And this is by Werner and de Wolf from 15. So you see that if for a fixed finite field, if L is logarithmic in K, and N could be polynomial or linear in K. There's no good lower bound. So there might be a construction like this. So if you allow the blocks to be logarithmic in K, it's not that big. As far as we know, there could be codes that are very, very efficient. You can have logarithmic communication. So there's no lower bound. And that's for two squares. So, and then there's another lower bound when L is small and the field is small. That's a special. This is special again for the setting of linear codes. So if the field is small, let's say if you have a field of size Q, you can also the kind of easy lower bound. So I'm stating it for the code. So N is at least 2 to the K over Q to the L. And this is trivial. I think it's basically you basically say, okay, let's replace each block with all the just replace each. Okay, here it's easier to see it. Replace each subspace with all of the vectors in the subspace. So you get a list of size n times Q to the L. And now you get a 2-query code without blocks, but your delta dropped from a constant to 1 over Q to the L. Because your matchings are now, you replaced each subspace with a huge list of things. So now if you had a matching, an edge here, you replace it with some edge here. It's just one. You just get one edge per edge. So your delta is now 1 over Q to the L, and this is the bound for 2-query code. So your delta is 1 over Q to the L. So this is where you get this. And as far as I know, this is the best kind of.
Is that 2 to the square root of log K? Or
2 to the 2, where?
is a double explanation square root of the block length? Or is it just a single?
Here?
Yes.
Here, n is 2 to the square root log K. N is 2 to the L. So the log n and L are about the same.
The upper bound and the lower bound seem to contradict each other.
Oh, sorry. It's double exponential. Yes. Wait. Sorry. Yes, thank you. Wait, so L, yes, L is log K. So that would be the communication. Okay, sorry. Yes. Thank you. Very important. Otherwise, it doesn't make any sense. Right. So the prior to this construction, the best thing was K to the 1/3, and this was the first to be sub-polynomial communication. Right. So let me finish before we do a little break. Let me state a question, an open problem when L is 2 and the field is large. If L is 2 and the field is large, this already is meaningless, right? It doesn't give you anything good. It's an open problem. Pick large F, maybe infinite. They're real numbers. And And suppose you have n lines that are pairwise skewed lines. So pairwise, I guess, don't have to be, not pairwise. Okay, let's just leave it. And for every I, if you look at the projections, you can project it along the ith axis and you get another family of lines. Yes. Pi n. So for any projection, these lines have a linear number pairwise disjoint intersections. So there's an intersection, there's another intersection, there's another intersection. And the linear number, and every line is in one of them. Not every line, but every line is in at most one intersection. So you don't want to have one line with many intersections on it. There's many pairwise disjoint for every direction. So there are no intersections here, not even at infinity. So they're kind of completely independent. And when you project them, you suddenly get many intersections. And show that n is at least k to the 2.1. So you can get quadratic using standard method that we'll see later. But anything better than quadratic is open. Again, when the field is large, when the field is small, you can apply this bound and you get something. Okay. So I think maybe we'll do a 5-minute break. Someone asked me in the break, and I forgot to say it, but when we look at LDCs, we don't even have existence proof. So for regular error-corrected codes, a random function is also a code, even a random linear function. But for LDCs, a random linear map or a random function are not going to have any local dependencies with anything. Everything will be very independent. So. When I say we don't have upper bounds, we don't even have, so the only thing we have our construction, there are no other arguments, probabilistic arguments, for example, that show existence. It would be very interesting to find ones. So now I'd like to talk about constructions for higher t, or t equals 3, 4, and so on. And then finish with kind of the general lower bounds. Right. So let's look at free query codes and try to generalize the Hadamard construction and see what we get. So the Hadamard code, you think of x as a linear function and you evaluate it over a big set. You evaluate it over all 0, 1 vectors. So to get free query codes, one way, but we'll see a better way later, but the simplest way is to look at, let's first fix the field just for simplicity to be a small finite field with no more than with these 4 elements. So let's make it F5. And we'll think of the input x as a quadratic function. So quadratic function has, it's over L variables has, think about a multilinear quadratic function has two, L choose two coefficients. So we think of the message x as a quadratic form, it's called qx on L variables. That's just described by x. So now I have, let's say x is given by two indices, ij. And but I think of my message as quadratic, and my code, E of x, is just the evaluations of this thing. Let's say this is why we want the field to be small. We just take the evaluations everywhere. So my n is 5 to the L, which is, omitting all the constants, is just exponential in square root of k. So instead of exponential in k, we get exponential in square root of k. And we'll see that this is a 3-query. This is very nice. You can take bigger fields if you want. I'm just doing this to simplify things. So why is this a 3-query code? So what's the decoder? We're trying to decode some particular coordinate in x. In this case, it's a coefficient of one monomial. So this will be, in particular, it's the value of qx at some particular point. Let's call it Pij, which is just Ei plus Ej. Right? So it's the value at some point. So how do you recover the value of a polynomial at a point? You pass you're a complexity theorist, you pass a random line, right? And you decode along the line. This is what we do. And so you pick a random line. Down through this point. This is the point. Take a line. Then we look at three random points on the line. The restriction of this quadratic form to the line is also at most quadratic. It's a polynomial of degree at most 2. So if I have the values at 3 points, I can recover the values on the other points on the line. And if you think of it, if you partition, you can kind of partition the space into all the lines through the point, you get a matching that covers almost everything. So on the code, basically we can recover the restriction to the line from 3 values. So this is pretty standard. This is called the Reed-Miller code of degree 2. And okay, so this is clear. All right, good. So for a long time, this was the best thing known for several decades. It was conjectured to be, maybe the optimal thing. It's very clean. You know the Hadamard is tight, and then you get this. So this is probably tight too. And this was a big shock when it was proven that this is false. So this guy, can we do better? And So the first paper was the big breakthrough was the paper of Buchanan. So go 8. Buchanan gave this framework for constructing LDCs that was different than this. And there was a component in its construction that you needed to rely on the fact that there are infinitely many Mersenne effect, the conjecture that there are infinitely many Mersenne primes. And then quickly after Fermento removed this requirement. And showed kind of how to really get codes that are much better than this without any number theoretic conjectures. And these are called matching vector codes. And these give the best construction that we know until now. And I'd like to show you the construction. So first we need something called a matching vector family. Matching vector family of size k in set m to the L. So Zm, I use this for the integers mod m. So a matching vector family of size k in this space is a pair of tuples. So you have up to u k and w1 up to wk. Each element is here. So these are tuples of integers mod m. So there are 2 tuples and they're numbered such that the inner products ui wj are such that there is 0 mod m I is equal to j and non-zero mod m I is not equal to j. So the inner products, the matching inner products are 0 and the crossing inner products are non-zero mod m. The question is, so you'd like a family that's as big as possible under these conditions. So I mentioned in the abstract set systems with restricted intersections. So if these are vectors, if the vectors themselves are 0, 1 vectors, so you can think of them as sets, then these inner products are just the sizes of the intersection, and then it's a question that people have been studying for I think 40 more years. But this is kind of slightly more general, even though you can always go back to sets. You can encode it back as sets if you would like, so it's not really different. The famous paper of Frankel Wilson really studied this and showed bounds, and we'll mention one of the bounds. And so this the theorem that I'll show you, which gives these codes, and it's really in a Fermenko's paper, but it builds on all the stuff in Buchanan's paper, is that if you have a matching vector family of size k and set m to the L, then if there exists such a family, then there exists, we can use this family to construct the code an M query LDC f to the k to f to m to the L, where f is any field such that there exists a gamma of order. There needs to be an element of multiplicative order m. So you can take the complex number, for example, you can take many finite fields and so on. And you need this element. Okay, it's really surprising and it's really cool. And it's not very complicated just to prove this. And a corollary, so this is the big kind of surprise, is that we'll talk about what's upper and lower bounds known for this size of this family, but currently the best construction of codes, and I'll just state it for 3 queries now, is that it's based on the result of Grommush. This is a really amazing construction. So Grommush constructed the matching vector family. For example, you can take Z6 to the L. So see later that you need M to be composite to get kind of interesting families. So the smallest composite where this works is Z6. So again, this is a special case of a more general thing, but there's a family in Z6 to the L of size K, which is up to constants exponential. Hopefully I'm not messing up the number of exponentials here. Okay, so you can construct a family in Z6 to the L that has size, well, it's super polynomial in L. From this, you get, using that theorem, so you get a 6 query code. So you can actually reduce this to 3. That's an extra trick that reduces it to 3, but the standard reduction gives 6. With n, x square root log k log k, which is, if you think about it, it's less than 2 to the k to the epsilon for any epsilon. So it's not just better than the exponential in square root k, it's better than exponential in any polynomial in k. So it's better than any constant query code from that construction. Even if you take higher degree thing, this 3 query code is just better than all of them. Okay. All right, so questions before I show the construction? Construction is very, very simple.
What do you mean it's better than any?
So you can take this quadratic thing and do it with cubic polynomials.
I see.
So you get 4 query codes with x. In general, yeah, you get k to the 1 over t minus 1. So this will be better than any constant query code from this family. All right. So let's see the construction. Questions? Construction. Now I'm assuming I have such a family, and that I have a field with an element of order m. let come to the order M. Common to them is 1 and no lower power is 1. Again, we're going to think of X, interpret X as a function. So if X is an F, okay, we define a function associated with F, with Fx. Now it's a function from Zm to the L to F. And the function is X of Z. Now Z is in Zm to the L. Sum goes from 1 k xi comma to the inner product of ui. But the ui's are the vectors at the top. So you take this family, you use the top row for the encoding and use the bottom row for decoding. So you can think of the Fourier transform of this group. We have a matrix with this Z X, right? This is the Fourier transform matrix of this group over this field. And we're basically saying the generating matrix of this code, oh, I didn't say what the code is. The code with X is just evaluations everywhere. X Z. So it's a code from F to the K to F to the M to the L. These are the columns. So what is this thing? You're taking a linear combination of the columns that are indexed by this matching vector family. All right. So I'm taking this times x1. So the Z is the evaluation. So for every row, I get the evaluation. But if I just look at the if I represent this function as the column vector of all of its evaluations, it's just a linear combination of this thing. So really the generating matrix of the code is just take the columns of the Fourier transform indexed by the UIs. And this gives you a matrix that's K by N to the L. And that's the rows are the VIs in the structure. So it's a really simple thing. And what's the decoding? How do you decode? So I'm trying to recover one of the coefficients in this function by querying it in a few random locations. So the nice thing about this, so maybe intuitively, I'm taking combination of these phase functions, these frequencies. It's like sines, right, with different frequencies. And I know that there are these matching frequencies, WIs, such that with this inner product. So some of the if you look in direction W1, all the other frequencies will cancel. If you look at if you sum along direction WI, because the inner products are non-zero, and non-zero inner products cancel here because it's a cyclic group. But the one that's matching has inner product 0, and inner product 0 cannot cancel. So everything else will cancel except for this frequency. So this is kind of the intuition why you need those inner products. So let's see it formally. So how do you decode? Decoding, let's say xi star. Let's pick some because I'm going to sum over all the i's. So I want to fix this I star as the one that I'm trying to recover. Take a random line L. So line in direction, line here, in direction, WI star. L is some A plus lambda WI star, lambda with M. For A, I choose A uniformly at random. Let me just sum the function over this line. So again, it's a random, these are parallel lines that cover the space uniformly. So I just sum over one of them. So, so there's a natural matching here of n tuples. So just have to show that from these values I can recover xi star. Okay, so what's the summation? Get sum over lambda fx a plus lambda wi star. If I can get it all to fit here. So, and this is sum over lambda. Sum over I. I. Comma. A plus I. UI. So I'm summing over the I here, but this WI star is the one that I'm trying to decode. I'll change the summation. I get sum over I. Xi, comma, so the A and the UI come outside. And here, I get sum over lambda, W star UI. What is this thing? This is a 0 if the inner product is non-zero. And otherwise it's M. So yeah, it's M Xi star run to the A UI star. It's a multiple of Xi, so I can divide by. I know this is the things. As the decoder knows that. The decoder chooses A, so you just divide by it. Okay. You can do this over the complex numbers, everything will be just the same. Good. So again, there's a trick you can add on top of this to reduce the queries further. So let's say from 6 to 3. And I don't want to write down the whole thing, but instead of summing, I can sum with coefficients. So what is summing with coefficients? I'm going to end up with some coefficients here. So what is this? This will be a polynomial evaluated at roots of unity. So this polynomial is just the sum of powers. I can take a look at other polynomials. Preferably sparse polynomials, polynomials with a few non-zero coefficients. So this will reduce the number of queries. So I need a sparse polynomial that doesn't vanish at 1, but vanishes at all the other roots of unity that show up here. So then you need this extra level of complication where you say, here, instead of saying they're non-zero, I'm going to ask them to be in some special small set. And then I'm going to find a sparse polynomial that vanishes on these roots of unity and doesn't vanish on one. So there's like a second level of sophistication on top of that. And to go from 6 to 3, you actually, the only way we know how to do this, the Sefermenko did it, is to take the composite number of 511, and you do a computer search and you find such a sparse polynomial with 3 coefficients. There's a computer search, and it's kind of a very unique construction that's maybe, there's a paper that shows you can generalize this construction assuming some number theoretic assumptions like Mercent primes and so on, but it gets into kind of number theoretic stuff. But still, even without these tricks, you can always reduce the number of queries to 2 to the number of prime factors of M. So this, you can easily go from 6 to 4, because 6 is 2 times 3, so it's 2 to the 2. But to go from 4 to 3, you need this extra stuff. But anyway, I don't want to go into all that. That stuff. All right. So now the obvious question is, okay, well, what can we show about matching vector? Well, what's known about matching vector families? Are there lower bounds? Can we show that this construction cannot be too good? What's the state of the art in terms of our knowledge of matching vector families? It's like it's a sub question. It's not general locally decodable codes. You can just ask about matching vector families. Maybe we can show lower bounds. In this case, an upper bound on the size of the family would be a lower bound on the size of the code. So even there, we don't really know. Even though the gaps are gigantic. So let's just focus for now, for this talk, on M, which is a constant. You can look at growing M, and then we actually know exactly what the answer is, but when M is really big. But for constant M, we need this for constant M. So this is the interesting regime. So the first thing is that if M is prime power, then you can't do anything really good. So then K is at most L to the M minus 1, which in our world it's polynomial in L. And polynomial in L will not give you, so it'll be something, polynomial in L goes to exponential in L. So it will be in the setting of these Reed-Miller codes, like X is something polynomial. And this is Frankel-Wilson. They did it for set families. Maybe this is slightly more general. I'm not sure exactly from which paper, but the technique is, I can say about what the technique is in a few words. It's matching vector family is essentially a construction of a matrix that has zeros on the diagonal, non-zeros off the diagonal, and rank K, and it's well, n by n. If you give me an n by n matrix with rank K, so the rank here is over Zm. So we have to say, well, what is the rank over the ring? But you can define it, for example, as the smallest decomposition as K by n and n by k matrix. Right, because this will just be, you put the UIs here, and I's. And this will just be the matrix of all the inner products. So you can think of this as, what's this? No. proving an upper bound here is showing that any matrix with zeros on the diagonal and non-zeros off the diagonal has to have high rank. Right, so to prove this, let's say for prime, you can just take all the entries of the matrix, all the entries of the matrix, J, and replace them with their p-1 power. So the off-diagonal ones will be 1, and the diagonal ones will be 0. And when you take a power of all the entries of a matrix, the rank can also grow by at most that power. So the rank can go from R to the p-1. But the matrix with all ones and zeros on the diagonal is high rank, it's almost full rank. So it means the original matrix had to have rank n to the 1 over n-1. So this is how you get this power for prime. For prime power, you have to do something slightly more. So prime power doesn't work. And this is tight, by the way, because you can take these to be indicator vectors of all the sets of size n-1, and the wi's to be their complements. And then the inner products are 0, and the diagonal is non-zero. And then when M is composite, so again, there's this Grolmusch. So let me just state it more generally. So if M has R prime factors, so distinct prime factors, you can get a family of size exponential log L R over log L R-1. So that's the best construction. And the best upper bounds, so upper bounds on the size of the family are kind of lower bounds on the code. Best upper bound for composite, that's pretty embarrassing. So there's unconditionally, the best upper bound is O of M to the L over 2. Actually, L over 2 plus a constant here, like 8. This is with joint work with a former student, Guang Dehu, years ago. So this is consistent with the quadratic LDC, right? Because the code is from K symbols to M to the L symbols. So if K is M to the L over 2, it's basically quadratic. This is unconditional. If you assume a number theoretic conjecture called the polynomial Feynman-Ruscha conjecture, and you assume that it also holds in Zm, which is an even more, it's a conjecture in additive combinatorics, then you can show exponential in L over log L, which is slightly better. This is a paper with Baumick and Lovet. Again, assuming whatever this conjecture is, it's stated in the Tao Wu book, so it must be correct. You get sub-exponential upper bound, which means like a super polynomial lower bound on the code, assuming no other trickery. So kind of the straightforward construction of the code would be, would have to be super polynomial, if the PFR thing is true. And then, this leads me to the last thing I want to talk about. So I said this is consistent with the quadratic LDC. However, there's a recent cubic lower bound for 3 query LDCs, which say that it's for this lower bound is stated for binary alphabet, but the authors say you can probably actually extend it to bigger alphabets, and then using that lower bound, which I'll mention. So let's say if you had a 3 query lower bound, a cubic lower bound, you would get an upper bound of the form k is at most m to the L/3 for those m that give a 3 query code. So, and we know, for example, that for m equals 511, these constructions can be used to give a 3 query code. So again, using this new result that I'll mention, you could improve this from L/2 to L/3 for specific values of m. So again, this is just a comment. All right, so any questions on this? So I'll try to finish in the next 10 minutes, just to say what are the lower bounds for for general LDCs. So first, let me just state what's known, and then we'll see a sketch of at least one of the proofs. So the first paper is to look at this was Katz and Trevisan in 2000. And they show that n is, and omitting logarithmic factors, k 1 plus over t minus 1. And the technique is very general, so it really holds for any field. So if t is 3, k to the 1.5, then it goes. So at least we know that for constant number of queries, you can have a linear code. You can have a good code, constant rate. Right, so it already separates it from standard error code. Then there are a couple of papers. So this is Kerenidis and the Wolf and Woodruff. You have a small improvement here. They show that k to the 1 plus 2 over t minus 1, if t is odd, and k to the 1 plus 2 over t minus 2, t is even. And this is for binary. Stated for small fields. This is also for better for nonlinear codes. So also this. So let's say for 3 queries now we already get quadratic bound, and also for 4. So that's and then the really surprising recent result by Al-Rabia, Guruswamy, Kotari, and Manohar, 22. They showed for t equals 3, and up to logarithmic factors, they show the cubic lower bound. So small. Again, this is also for nonlinear. And so they state it for binary alphabet, but they say you can probably generalize it for small enough alphabets. So let's say if the alphabet is a subpolynomial, let's say in k or something like that. So this is it. So again, even this, so this took many years, and it's a really difficult paper. There's a lot of stuff here. This is still really far from the upper bound. The upper bound is like 2 to the k to the little of 1. But yeah, it still took a lot of work. And so I don't have a lot of time. I just want to show something about maybe how to get how are these bounds proven, at least the basic ones. So that's just the proof sketch of so if you wanted to prove that n is at least k to the 1.5 when t is 3. This is the basic kind of Katz-Travis-Sun proof. And so you have these vectors and you have matchings, mi. And so for every I, you have this matching. So this is one matching, this is another matching. They're big, right? So the basic trick is just to say that, okay, I can find a small set that contains one element, contains one tuple from each matching. So how big would such a set be? So again, if you take a random set, it's essentially the best you can do, you need to take something roughly n to the 2/3, up to logarithmic factors. So there exists a set of size roughly n to the 2/3 containing at least one tuple t in each mi. So if you pick a random set of this size, so that you sample each element with probability n to the -1/3. Each tuple is chosen with probability 1/n. So an expectation you have to see one in each. So if you had a couple of logs, or you'd get one in each. Why is this? Because I'm saying from this set, I can recover my message. So if you just give me the encoding restricted to this set with no errors, there's a tuple recovering xi for each I, so it's invertible on this set. So k is at most, so e from f to the k, so that's e restricted to s is invertible. So k is at least the size of s, so k is at least n to the 2/3, so n is at least k to the 1.5. And you can't hope to improve this. So one way to try to improve this is to say, okay, maybe if we knew something extra about the structure of these matchings, we could improve it. But if you don't know anything about the matchings, take random matchings, then this would be the size that you would need to get one from each. That's just same counting. So this really doesn't use anything about so to improve this to quadratic, you can use the fact that we have really strong two-query lower bounds. So you can try to reduce this code to a two-query code. And so this is again a sketch of how to prove a quadratic lower bound. Oh, I forgot to mention here, there's a paper of Woodruff that shows n is at least k squared for any field for linear codes for t equals 3. So this result, it's not this proof, it's a slightly simpler proof that I can't remember where I saw it. But the idea is really simple. So again, we have these BIs and the matchings. This other matching. The idea is to find a small set S that hits one element. This is not a good drawing. I want a set S that contains one element from many tuples in each mi. So somehow, if I could erase those coordinates, I would get a two-query code. So this is the idea. So you can show, say, if I just want to find one element in many tuples in each mi, I can get a smaller set. So you can find a set S. Like in this case, I want to take something like square root n. Just to be safe, I'm taking 2 logs. You can do this without any logs if you work harder, but let's just take as many logs as we need. So if you take such a set, it would it gets at least square root n log n tuples, the edges in each mi. And when I say hits, I mean it has at least one element in at least square root n log n tuples in each mi. So again, this is just for a random set. We can give you that. So what can I do? How can I get rid of these coordinates? I'd like to throw these away and get a two-query code with where the matchings are slightly bigger than square root n log n, which is what I need to get a lower bound. But if you use the exponential lower bound, this would still give you something meaningful. So what you do, you can project this set to 0. And I don't want to do all the details. We're almost out of time. What you do, you find a linear map that sends these VIs, these VJs in S to 0, and keeps the rank as high as possible. So you can assume that K is at least 2S. Otherwise, you're done. Otherwise, this is what you're trying to prove. If K is square root of n, then this is what we're trying to show. So let's say K is bigger. Let's say K is twice the size of S. I can send S to 0. I can send everything in S to 0 and keep the rank of the other vectors at least K over 2. Because it's a small set. So I take everything that's not in the span and I keep it independent. So basically, I can project this to 0 and still keep a code with K over 2 independent coordinates. But now, if these 3 things, or if these had EI in their span before, now one of them is 0. So I only have to read the 2 that are not 0. So I get a two-query code. You get a 2 LDC, where the size of the new matchings is something like this. So I only keep the tuples where I hit one of the 3. And then you have you use this lower bound. So what is delta here? Delta is log n over square root n. Sorry, log n over log n over square root n, right? Because the size of mi is delta n. And then if you plug it here, and again, K, you can assume K is at least some big multiple of square root n, you get a contradiction. So this lower bound is just strong enough to handle matchings that are close to square root. If I didn't have the log n, I couldn't get anything, because then I could just take disjoint. The matchings could just be disjoint. But if they're slightly bigger than square root n, they have to overlap, and then this lower bound already kicks in. So that's again, this is the best lower bound for general fields for 3 queries. And I don't have time to talk about this thing. I also don't fully understand it, but it's for nonlinear codes, and it's very, very sophisticated. So it's more in the information theoretic kind of world where you're looking at correlations connections to CSPs and hardness of approximation. It's a whole different. Okay, that's all I have. Thank you.
Sorry, I was starting this construction with the gamut of the inner product stuff. Is there any convoluted way to see this as part in the framework of the construction you did just before this algebraic geometry thing, when you sort of taking polynomials and evaluating them points? It feels like you're sort of evaluating on a tangent plane or something.
Kind of. So you can think of these as polynomials evaluated at roots of unity. But you can think of the polynomial whose exponents are the UIs. So each UI is a tuple. So you can think of a monomial that x1 to the first element, x2 to the second element. And then you're just evaluating them at, so these are really polynomials, but they're not low degree polynomials. They're polynomials whose monomials are indexed by these. And you're evaluating them over special sets. And the lines, they're not lines, they're like geometric lines, they're exponential. But actually, in this view, so we have another paper that does this. You can actually get the inner product here to be small, like less than m over 4. If you do some tricks, it's not very hard. You can take any matching vector family and get a matching vector family where these are, if they're non-zero, they're not too big. And then you can actually use this to do this construction when m is super constant, where you have to do some additional correction so that the queries are not going to be all correct. So you can kind of think of this also as low degree polynomials somewhere. Yeah.
But there's no, I think you didn't say how you say how you find these families, but there's no way of thinking about that construction of the family that we know of in terms of some sort of geometric, polynomial connectivity roots.
Yeah, the construction is really strange. I mean, it uses something called a low degree weak representation of the OR functions. So you can think of you can try to find a polynomial over Zm, multivariate polynomial that vanishes only in the origin and has low degree. So this was done in a paper of Barrington, Rudish, and forgetting. So this was done in complexity theory for other reasons, for looking at circuits with modular gates. And using that, Gromush uses that as a black box. So somehow, and the construction is a little strange. It uses Lucas theorem, but it's there's no like deep theory or anything that I can say. Oh, this comes from some famous theorem or anything. It's very ad hoc. I think. The questions?